Continue this afternoon session with Rafael Gonzalez from Universidad del Norte in Barranquilla, a colleague of mine, the one that brought me to this world of condensed matter physics. Rafael studied in Bogota in the National University, his PhD, and since then has been working in Barranquilla. And he has good collaborators in Mainz, the Sinova group. Rafael, thank you for
the introduction, and thank you all to be here. Thank you for the Institute to accept our idea of this workshop. I'm going to talk today about the spin topology in insulator materials. And I'm going to talk the story about that. We start with this really weird material, mutation iron oxide. I was studying the non-relativistic Einstein effect in this material. It's no collinear antiferromagnet. And I noticed that the material has a quantum spin Hall effect or spin Hall effect signal in the bandgap, inside the bandgap. And I asked to Bernardo, please help me with that. Bernardo said, okay, let's calculate the spin Chern number. We calculate the spin Chern number, but we don't find any relationship. I remember that we found a number and a number, but we don't have connection with the signal. And then we make a toy model and calculate also the spin topology. It's maybe the spin, we plot the spin as a function of the K vector in the reciprocal space. It's the spin spectrum, we call that. And finally, we don't find nothing to explain the spin body in this material. But unfortunately, this path give really nice words with Bernardo. Maybe 1.5 years of work. We finished with this spin-wide topological insulator. I'm going to talk about this work. And we recently, just 2 days ago, we put this in archive. That is the average spin Chern number. This is the outline of my talk. I'm going to talk about this today. Okay, fortunately, we talked this morning about this phenomenon. This is the Hall family. We have the anomalous, the normal Hall effect, and the quantum Hall effect, and the spin Hall, quantum spin Hall, anomalous Hall, and quantum anomalous Hall effect. And we can go faster here. We saw, actually, Bernardo presented this work also yesterday, that we have the first connection with the topology was this anomalous Hall conductance with the spin Chern number, with the Chern number, the first Chern number. And we saw also this plot this morning about the relationship with the perpendicular conductivity with the Chern number. And after that, maybe a few years ago, the professor has made a really nice high banding model to describe one way to open the gap, a different way to open a band gap in hexagonal lattice, and we found this quantum anomalous Hall effect. If we solve this model, simple model with just interaction terms, the on-site term, first neighborhood interaction, and the second one, and we can plot the band structure here, and also the anomalous Hall effect, and we saw that it's a really connection with the Chern number and anomalous Hall. Then finally, we have this spin Hall effect, and this was the quantum spin Hall effect was observed in these manganese telluride layers, manganese telluride quantum wells, and we saw that in the experiment we have some regime when we have the fan inversion in this kind of material, and for B larger than 0.3 nanometers, we can see the quantized conductance which means the quantum spin Hall effect, the first measure of this quantum. And for less of this distance or this thickness, we don't see we have a trivial, or we see this conductance of spin Hall conductance. And the way to characterize the topological matter in this way is measure the conductances, in this case the spin conductance, so we see the signal in the bandgap. How is the value in this bandgap? And for describe this experiment in this paper, the Bernardo Uribe and Sang proposed this model that is a 4-band model. And we have a S-type and P-type orbitals that is named E and H, and we can have the spin up and spin down by functions. And we have also here the Hamiltonian, like similar to the Haldane, is two copies of the Haldane model. And we have here the results of the parameters for the Calmi telluride quantum dots. I'm going to start with this model, with this simple model, the 2D VHC model. And we are going to calculate, for example, our spin Hall effect. First, let's check what is the phase diagram for this model. And we can, for example, calculate the eigenvalues. And the eigenvalues show that we can close the gap just when these two eigenvalues, they are double degenerate. The eigenvalues should be equal. The only way is all of them are positive is that they will be zero, sorry. And in this case, we have 4 possibilities or 3 band crossings in the phase diagram of this material, of this model, sorry. For example, we need to sin of kx and sin of ky to be 0, and n equal to 0 to have this eigenvalue 0 equal to the other ones. And the other ways have here -2 or 0 or 2. Actually, we have 2 options here with 0. And in these cases, for this value, the model predicts energy spectrum is gap. Sorry, for any value of m over p is the spectrum is gap, except for this particular points. Okay, we calculate the band structure for different m over b parameters, and we can see that we have always got material just when we cross in m over b equals 0 or m over b equals 2. And this is also the prediction from the theoretical point of view. And here we have actually m equals 2 and m equals 1. And we saw the difference in this.
Rafael?
Yeah.
There's only 2 bands here, or they're double degenerate?
They are double degenerate. We have 4 bands. It's double degenerate. We have inversion symmetry and time reversion. And then, okay, we have defined the spin matrix. The spin matrix is like here. We have 2 sections, 2 copies of the Haldane model, and we calculate the spin Hall effect. I think one of the properties that I like to calculate is the spin Hall effect and the anomalous Hall. And we use the Kuo formula for these calculations, and we can see we use this operator for the current operator, and this is the similar formula for the anomalous Hall, just we introduce this spin current operator. Yeah.
How do you consider the double degeneracy bands?
The double degeneracy?
Yeah, for the summation, I'm not able to have what it both m and n.
We use here this n different to n, always for this calculation.
In DC case.
Huh?
In DC case, omega equals 0.
Yeah, this case. But we have problem. Sometimes we have problem with the convergence of this quantity. We introduce some parameter noise just for numerical, and we convert with this parameter to have a correct answer for this problem. And if we calculate the spin Hall conductivity, we see, for example, that the case of m over b larger than 2, we have no signal in the inside of the bandgap. I will calculate, for example, for one of the values of m, for example, m equals 1, we have a signal that corresponds also quantized quantum spin Hall conductivity in 2-dimensional system. And the quantization is going to, we have this property, the spin and the Hamiltonian are, the spin is a good quantum number because we don't have mixing of the spin in the material, in the model. And if we compare with for example, 2D materials that in this paper, we have results for Stanin or Germanin that we have also really close values of the quantized quantum spin Hall effect in some materials. In other materials, maybe the difference should be largest, that the should be due to the node is not always perceived with this quantity in the real material.
So you have the spin orbit coupling in the DFT.
In the DFT, we have the spin orbit coupling. Yeah. It's the only way that we have signal in the spin conductivity. Contradictory, we need the spin orbit coupling to calculate the spin conductivity.
That's the reason it's not exact.
That is the reason that it's not exact. Now let's go to the spin topology. What is this concept of spin topology? And let's start with the band structure of the BSC model, 2D system. We have double degenerate bands. And let's forget of our conduction bands. Let's focus just on the valence band. And let's calculate and use the work of Professor Todan about we can separate the conduction of the valence bands because we have energy gap. And we can project the wave functions and the spin operator only in the valence band. We construct this matrix that should be the spin matrix, similar to the spin operator projector. That is, we have the wave functions and we have our operator, but these wave functions are only the valence bands. And we can construct, if we diagonalize this matrix, we can construct the spin balance spectrum of our operator in the reciprocal space. And this is what we call band topology, and the idea is try to extract the invariants of this new spectrum. In this case, we know that each point in this model represents up and down electrons, and we solve the matrix. We find the eigenvalues of the spin operator and eigenvectors. We have two sets of wave functions, the up and down wave functions, and we obtain a perfect one in these units. There is one in these units that represents that the band is completely up and down character for the full Williamson or for the full band. We expect that because we don't have spin orbit coupling in the system. Recently, the spin spectrum was also studied in this nice work of Nature Communication, published this year. And one of the properties of this spin spectrum is describe the occupied state and could complement the information of the band structure. This spectrum have characteristics like it's given on the inversion symmetry, because we know that the inversion symmetry don't affect the spin C property. It's all on the time reversal symmetry and satisfy the relationship for the combination of time reversal and inversion. Okay, that this should be a really complementary help to understand the invariants and the information in the topological information in the bands. Let's use this tool to describe our invariants. Okay, we have again our spectrum. If we include spin orbit coupling, we hope that we have a little perturbation of the -1 and 1 eigenvalues of the spin operator, and we can calculate the very curvature up for the up wave function and for the down wave functions in the separate way, and calculate the spin up Chern number and the spin down Chern number from this wave function of the spin operator. We know that these two copies of the spin Chern numbers could add the information also of the spin up and spin down conductivities in the sample. For example, we have here that each of one are connected by time reversal, means that we have two opposite currents in the material, and the transversal ones, and we can connect this spin Chern number with the C2 invariant and also with the spin Hall conductivity. Here we can define we can define the spin Chern number like a subtraction of the up and down Chern number over 2, and we can define our spin Chern number like 1 for up and 1 for down channel. Yeah. And okay, we can start to connect this with the C2 and the spin Hall conductivity that we had before. Let's start first with the BSC model. And in the BSC model, we can calculate the spin Hall conductivity like with the common formula. And we have our 0 in the trivial case, minus infinity to minus 2. After that, we have minus 1 to the formula, and then 1, and then again 0 for the trivial case. We have the for region in reality, the same region that we discovered with the eigenvalues. And we calculate also the spin Chern number, and in this case, the spin Hall conductivity and the spin Chern number coincide one on top of the other. One of the characteristics of these 2D material and this 2D material without the spin of the couple, we don't have mixing here. Actually, we can include some mixing with break time reversal and break inversion symmetry, for example, and we have noticed that we have the same phase diagram in this plot. Okay, here we have a really direct connection between the spin Hall conductivity and the spin Chern number. And we can characterize our topological state with the spin Chern number calculation, or with the spin Hall conductivity with the co-formula, or with in this way. Okay, we also, to test that we are correct, we have the proper wave functions.
Sorry, in the previous case, the spin Hall effect is non-zero,
The spin Hall effect is not 0.
but you have no spin over coupling.
Without this is without spin recoupling.
So how did you get a spin Hall effect without the spin over coupling?
It's because you have 2 copies of the Aldane model. You have a spin Chern number. We have a Chern number for up for this one, and Chern number down for this channel, and we can see the spin recoupling. We can see, sorry, the signal spin Hall conductivity with the spin Chern number. We have if you calculate the spin Chern number for up or for down, you have this is 1 and this is minus 1, and you have that the spin Chern number is equal to 0. And if you compare with this formula, it's really similar the calculation, and you saw that it's spin Hall conductivity is the same thing. Maybe we can clear later in the 3D case. And also we can calculate the C2 invariant with the Wilson loop. We have here the trivial cases and here the trivial case. And also we can see how it's represented with the parity of the wave functions. It's a simple model, it's 2-band model. We can calculate the parity of the wave function in different points of the region zone. And we can calculate also the C2 for this path. And okay, we calculate for directly with some loop of C2 calculation and for this parity. And we can see that we still have this 4th region of the phase diagram, where we have when we crossing from the trivial to the topological case, we change the eigenvalue of the wave function in this point, and when we cross for this region, we change x and y, and finally we can change the sign of the parity of the wave function in gamma. And yesterday, Bernardo demonstrated that it is possible to we can see the crossing of energy band when we change from one region of the spectrum of the phase diagram for Chern number equal 0 to Chern number equal -1. The only way to cross this border is crossing the bands, cross the information in the bands. And here in this case, we have the crossing in the endpoint, because it's the endpoint that is changing the parity just in this point. If we cross into these 2 regions, we have double crossing in X and M, and finally we plot the bands in this region. We have energy crossing in the gamma pole that we have here. This is a characteristic that we connect to topological material, one trivial and one other that is not trivial material here. And this the way that we saw in the manganese, in the mercury telluride quantum was this stays in the border, but because we had the connection with the topological and not topological. The question now is what happened in the 3D materials.
Before you go on, I was curious if you've considered any cases when Z2 invariant is trivial, but the spectra number is not.
No, here
Yeah, there's always okay.
we have only this case, but in 3D we can see that. We can see in 3D. This is the introduction to go to the 3D that is the main result. Thanks for the question. Let's go to the 3D materials. In 3D materials, we have different ways to characterize the topology. We can calculate the Chern invariant using the parity of the wave functions. Also, we can show how is the pan inversion if we project, for example, the bismuth p orbital is bismuth 2 element 3. And also, if we calculate the quantum spin-Hall effect, we have a signal in the bandgap inside the bandgap. And also, another way to characterize the topological state is plot the surface state, like we have here in this plot. This is one of the common materials, bismuth 2 element 3 or bismuth 2 element 3 is examples of topological materials, topological insulator materials. And the question here is the connection between the quantized spin-Hall conductivity here in the bandgap with the spin number in 3D materials. Because we saw now that it's directly in 3D material without the spin-Hall effect. This was the question with Bernardo, with what is the relationship with these two quantities. We start with the low energy model for bismuth 2 element 3, that is this kind of Hamiltonian, is 4x4 Hamiltonian that was described in this article, in this paper, this Nature paper, and they put the weight of the Hamiltonian, the shape of the Hamiltonian is similar to the BH model, just we need an extra component that is the C component. And they have also the parameters for simulate the bismuth 2 element 3 in the low energy mode. Let's use this to answer the question now. We can use this version of the BSC model in 3D. We have our M parameter, that is the on-site stagger parameter, and we have the second neighbor interaction. And we include now the C component in this parameter. We have our A, that is the neighbor interaction, and we include the D parameter, the D interaction. Spin-orbit coupling is related with this D because mixing the up and down electron, but this extra C component is due to preserve time reversal symmetry also. We have preserved time reversal and inversion symmetry, but we don't have preserved the C component of the spin. Let's calculate again the eigenvalues of the energy. Calculate the eigenvalues for this matrix, and we have that is m squared, a squared, b squared is the plus and minus of this lambda value, and we can find where is this zero, where these eigenvalues coincide, the valence and the conduction bands, and we can find now that we have 5, 1, 2, 3, 4, 5 region of the spectrum. In this case, sin k, sin kx, sin ky, sin kc should be 0, and it should be 0 again. The only option here is that we can have 3 minus 1 or 1, 1 minus 1, 3 options in this case, 3 options in this case, and 1 option in the other. If we chose these values, we close the bandgap. And we have here the other value of M over B, we have a gap energy. We have here the results, 3 topological cases, so this UPS model, and 2 trivial cases for M. In the region of M over B, sorry, the region for we call here the strong topological insulator, spin topological insulator. I'm going to explain what is the name here, this thing by topological insulator. And because we have the case when we have spin hole conductivity, but we don't have the system invariant in this case. Let's solve the problem. Let's choose one region of the M over B sub 0, and in value we have the gap energy band structure. But we noticed something really special in the spin spectrum that was really surprise to me. We obtain a band crossing in the band spectrum for this particular path from S to T, that is the path when we have Kx and Ky equal pi, each of 1. And we saw before with Bernardo this result because Bernardo talked yesterday about the bipoints. We studied bipoints in energy spectrum, and now we saw bipoints in the spin spectrum. And that was really interesting for us. And let's move the parameter. Let's move
I'm sorry, what's being plotted in the right?
here.
Yeah.
What's
the y-axis?
We have the spin spectrum. Here is the spin C component.
Okay.
Projected one.
The projecting
Projection, okay.
the projection spin C component. And for
So
this,
there's a singular point that in your projection, okay.
yes, we have a singular point in the projection that we find 0 spin component of in the valence band. Let's try for the other positions. For example, for these cases, for Kx equals 0 and Ky equal pi, or Kx equal pi and Ky equal 0, we can go from the y to y prime, and we found also for up and down, we found again our spin by point. This we call the spin by point, because this spin by point is the spin spectrum. And again, for the Kc equals 0, or these 2 zeros in the Kx and Ky, we obtain our 2 spin by points in the spin spectrum. And that is really interesting.
Also shows a certain path in the previous one. Do you think you missed some, or these are all?
That's a good question. Let me advance, because yes, Bernardo said yesterday. Yeah, yes, yeah.
Well, the model shows it only happens on the high temperature line. It's just close up.
Yes, it's
So
the
it's
high
the only
temperature.
place that's gonna happen.
Only the high temperature. To check that, let me explain what did after that. Okay, to be sure that we have this particular white points, we start calculating now the spin number. And we calculate the spin number for different Kc planes. We start to calculate for different planes, and we notice that the spin numbers start to change from 0 to 1, again to 0, along the Kc path, perpendicular Kc planes. That means that we have the signal of our spin by point. We saw with Bernardo in the energy spectrum that the only reason that we have this is because we have a chirality of this by point that generate very flux in the that is measured by spin very curvature and the spin channel. Okay, we start with the 0, start with 1, maintain 1, and start to change to 0 again, final to the Kc component. This means that we have a case for HKC, we have a different spin number, and then we also try for the other region of the phase diagram, and we notice, for example, here we notice that changed twice. That means that we have two point. That is what the way to be sure that we have just one point in the one spin by point.
So is the spin Chern number reflected in edge states?
Of the projected spin operator.
Generally, no.
Yeah, in the projected spin operator.
No, I don't think so.
Edge states. We need to cut the material.
Yeah, if we count the material in for these three regions, we notice the energy band crossing. For sure, we have an energy band crossing provided in this topological region, and if we change from here to here, we have a crossing, energy crossing here, we have an energy crossing here, here. Because we found that this is the condition that we have gapped it. Spectrum, energy spectrum is avoid these points. That means if we put this material in, it's put in contact with the insulator, we have an energy crossing. The important here, we discovered it with Bernardo, we have these spin by points in the spin spectrum. Really interesting result for us. And okay, let's use this information to classify or characterize our topological phases. And we had experience with the white point, with energy white point, but now we can start to use this experience with the spin spectrum. And we say, okay, this was idea of Bernardo, okay, let's characterize our phase with this spin Weyl indicator, that is the number of spin white points in the half of the driven zone, or take the absolute value of these chiralities and divide by 2. We have this indicator to characterize, for example, 0, 1, 2, 1, 0, the spin value indicator for these new phases. For this phase, okay, this is our model. Okay, let's Bernardo enjoy the mathematics. Let's go to the mathematics. I do the computer simulation. Bernardo start to calculate by hand the eigenvalues and calculate the eigenvector of these matrices and calculate the spin spectrum for the valence band, just for the two first states. And we say, okay, the only way that we have spin by points is because the spin spectrum is equal to 0. And by hand, we discovered that this happening with these conditions are complete. And in this case, if we solve this equation by hand, we found the position of the spin by points in the reciprocal space. And also found that it's possible to have two pairs of spin by points that are connected by time directed symmetry with opposite chirality. Okay, let's summarize this in the table. On the paper, we have these trivial phases. We have 0 for every spin. We have this topological phase that this is the position that Bernardo found of the spin by points, the coordinate of the spin by points, one for plus, one for minus in this in this particular coordinate. And also we can characterize the phase with the spin Chern number of the Kc equal pi, Kc equal 0, that is the spin Chern number of the top and bottom box, not the box, our driven zone. And also I can calculate the parity of the eigenvalues. So we have, for example, this point change in the parity of the eigenvalue. And for this we can calculate the spin value indicator and the few can email this invariant, also the C2 invariant is equal for 1 for this phase. And also we can describe, we noted that only the spin value indicator is not the only parameter where we need to describe the topological phase. With another extra numbers that in this case are the spin Chern numbers on the top and in the middle of the driven zone for k equal 0 and k equal 0, kc equal 5, and also for kx and ky component. In the middle of the spectrum, we have a really interesting result that we are asking now, that we have spin by point equal indicator equal 2, but we don't have the C2 invariance. It's principally not topological or strong topological phase, but according to how we have 2, should be stronger than the strong topological phase. We have 2 spin by points, spin indicator equal 2, and this is the location of the spin by points. 2 spin by points in case y and x coordinates, and finally the other region we have the plot distinction number, again a strong topological phase, and we have maybe we have one here. We have a mistake in the table. We have here, yes. Let's classify the material with these spin topological indicators. We can start with material. Obviously, we need a bandgap, or at least a separation of the valence and conduction bands. And we can split for this first Chern class is different to 0. We could have a Chern insulator is different equal to 0. We have could be a topological material. If we have a spin value indicator equal to 0, we don't have spin by point in the spin spectrum. But we can have quantum spin Hall effect still, like in 2D system, for example. We saw that in the 2D model we don't have spin value indicator, but we have a spin Chern number in this case. This we call spin Chern insulator. This is the spin insulator, normal insulator. But also our spin spectrum should have crossings. Like one crossing means that it's a strong topological insulator, and more than one should be spin by topological insulator. That is a way to classify the topological phases using the information in the spin spectrum. It's the only that we propose here in this. Okay, we have signal of the spin Hall conductivity. We have spin Hall Chern numbers or in these 3 regions, and we have the spin Hall indicator. This means that we should have also spin Hall conductivity in the region. And we calculate the spin Hall conductivity for these regions. And the idea is try to solve the first question, how connect the spin Hall conductivity with the spin Chern number in 3D materials. And okay, this is the example for N2 equal 1.5, where we find any value, and this is coordinates, but it makes no sense because we have also coupling. But let's try to explain the meaning of this value in 3D materials. The question is quantized, and the question is any relation with the 3D spin Chern number. And this was the last work that we did with Bernardo on the name is the average spin Chern number. Let's try to calculate again the spin Chern number by layers, in the case is space. And this is the definition of the spin Chern number. And let's sum up all the contribution for each space C plane. And our average spin Chern number should be in 3D the contribution of each scale layer to the total signal of the spin Hall conductivity. Here should be our average spin Chern number, that is sum up in some way the contribution of these KC planes. Integrate to pi, sorry, because it's the length of the Billion sum, and divide over to pi again. And in this case, we also, the idea is try to compare these results with the Kubo formula results in 3D materials. There are some relationship between two of them, the equation, and the answer is yes, there is a connection between these two quantities. And the connection for the case of spin-orbit coupling 0 was that it's connected directly, just one constant in front of the spin Chern number. Average spin Chern number is this quantity and the spin Hall conductivity is this number, and they are really directly connected without spin Hall decouple. These are our average extinction number, and this means that if you sum up all the contributions of this case C, should be related with the signal of spin Hall conductivity. Let me intrigue.
So is it basically the conductivity per layer?
Yeah,
Is that-
it's I sum up for each layer in case C space.
No, I mean layer in real space.
No, this is real layer but in reciprocal space.
But, so if I had a Chern number throughout the entire zone, so the average was 1,
Yeah,
then wouldn't you have a quantized spin Hall effect per layer in real space? So every layer would be like a
yeah,
quantized 2D. Because in 3D, of course, the conductivity has units of length, right?
yeah.
So
Yeah. This is, for example, here we have a constant value in the reciprocal space. We see, and for example, if one here, usually this change when we have spin by points. But if we don't have spin by points and we have, for example, a constant value of 1, it should be 1. Response. It's correct. Okay, I don't want to hear the material, but let's connect with some material. We calculate, for example, gallium arsenide. We plot the spin spectrum, and we have gap spin spectrum. We don't find spin by points. This is a trivial insulator, and we calculate the spin Hall conductivity and the average spin Chern number by frequency. And this is the case that you asked me. This is the case of this bromide. That is constant value of 4 for the full region zone, and the average extinction number is 4, and the spin Hall conductivity is 3.94. It's very close to the extinction number, average extinction. And finally, we calculate the average extinction number is any value, number, means that we have a spin by points.
and so what are the two numbers? So the 3.27, what
This is the spin Hall conductivity.
computed by the Kubo formula?
Computed at the form, and this is the average extinction number computed with extinction number. And we have here also for the nutritional field, we have the average extinction number and the spin Hall conductivity in the Kubo formula. And this means that it's not an integer number, and this means that we have a spin by points in the geometry. Now we calculate this average extinction number for each of the M over E region of the 3D BHC model. For example, for B close to 0, we have Bernardo found the position again of using the position of the spin by points. Using the position of the spin by points, he predicts how is the spin Hall conductivity, or actually what is the value of the average extinction number, because we know where is the position of the spin by points for each region and for each M over D0 in the spectrum. For example, for this region 4 minus 3 2 minus 1, here this equation represents the average extinction number using the position of the spin by points. This is this black line, and then this is the black line for this one. This is same functions, and this is the line for this. Now I try to contradict or see what will happen with Bernardo. I can calculate the average extinction number by hand for the 3D BHD model for different D values. D represents the spin of decoupling. And we notice, for example, that this signal is independent of the average to the spin of decoupling. The average extinction number is this black line, and depend only the position of the spin by points. And the position of the spin by points is independent of the spin of decoupling. That means that the average extinction number is the same for for every d value. That is really interesting results. On the other hand, we calculate the spin Hall conductivity for each case, and there is this dot line dots. And we saw in the limit of t equals 0, we have the coincidence of the spin Hall conductivity with average spin channel. This is a large spin orbit couplings in electron volts, but we notice that it's the same shape, that this is the Kubo formula, and this black is the average spin channel number using the definition of the spin numbers. And it's really interesting result because it's the first, the first time I saw the relationship in 3D of the spin Hall conductivity and the spin channel in 3D material. Here is 3D model. And this was a calculation before. We can divide the Kubo formula with, for example, the spin Hall conductivity calculated with the distance, because we know, for example, for anomalous Hall conductivity in various metal, the anomalous Hall conductivity is directly proportional to the distance of the spin by points. You can divide these two formulas, and we notice, for example, for small d, the spin Hall conductivity is directly proportional to the distance of the spin by point. And the final is that we measure with the average spin channel. We can also rotate the spin, for example, for different directions, and we can notice how change with the angle. We pass from C to X to C, and the black one is the average spin channel number with dots, and the lines represent the spin Hall conductivity. So this the shape is related with this formula for the spin Hall conductivity, and the average spin channel number is calculated for each angle. Okay, let's go now to the real materials. So the real material, we made a homemade code that is a combination of DFT calculation with Barnier Hamilton by the 19th, and the code PyTB, that is Python code to calculate type boundary models. We have this, our wave function is this basis. We diagonalize the spin matrix and calculate the very curvature with this very fluxivity in the code, and then calculate the spin channel number for each case. Actually, now in the literature, we can find two codes that use this spin topology. That's a new field, that is this nested and spin resolution loop code. With the people in the Nature paper, and also the very easy code that is a really fancy name. Very easy is the name of the code to calculate the spin resolver topology. They use a similar path to try to describe, but in particular in this, they don't use the spin channel number, they use the Wilson loop or the spin resolver Wilson loop to notice also the spin topology. Here we decided we took this neutral tree. We forget of the conduction bands. We know that we have up and down electrons, one on top of the other, because we have PT symmetry or P symmetry plus P symmetry, and we calculate the spin channel number for each layer in PC. And we have two bands to separate words. And if we don't include spin orbit coupling, the idea is to see something like that. But we expected, for example, with spin orbit coupling is included something perturbation in the spin spectrum. But the real calculation showed us again for the material, the real material, we have spin by points in the gamma T path, that is the diagonal path in the rhombohedral lattice. And this by point is means that we have this is all the balance state. If the balance state in this point is 0, means that the information of the spin is not in the valence band, it's in the conduction band. So this means that we could give at this spin by point, and this spectrum gives us the information to calculate values beyond the band structure or energy band structure. For the material, this is okay. This is a rhombohedral material, it's not too lattice. It's more in itself. We made again this calculation of the distinction number in different layers. And we obtain, for example, here how change the distinction number for different K layers, because we have a orthorhombical phase and we have this diagonal, the spin by points. We notice that the signal is present in the three axes. If we convert this to hexagonal, maybe we only see in the KC plane, because this material is hexagonal, but we can simulate with the rhombohedral because it's small units. This is the plot of the paper. We have this 2073, that is the signal spin for conductivity in the bandgap, and we found here our spin spectrum. This is the density material of the spin spectrum. That is means the only point that we own the signal of the spin is in this path T2 gamma. That is just the diagonal in the rhombohedral that connects also the c-axis in the layer in the hexagonal. We calculate for all these materials for 10 degree of tellurium. No, this is selenium. This is a mirror topological insulator. I forget it. Sorry. And we notice also extinction closing, that is this spin by point are really close one to the other. That means the signal of the spin by conductivity is really low compared with the spin the topological insulator.
This is topological also.
This is topological, yes.
But
This crystal topological insulator is the name of this, because we have a mirror Chern number. We know that in topology we have different names to classify materials. We have, for example, this is topological crystal insulator, but we have also this that is iron topological insulator, for example. But we can use the information of the spin, our spin indicator or the spin vector indicator to characterize these phases in another way. Because now we have different names. For example, this topological, crystal topological insulator could be also characterized with this spin topology. For example, for non-band insulator, we don't have spin numbers and spin indicator. We don't have spin by points. For bismuth, for example, we don't have spin by points, but we have spin Chern numbers in all the phases of the material. Sometimes this is called higher topological insulator, for example, the bismuth. This material, for example, has 4 spin by points, and this is the Chern number of different layers. So this is our strong topological insulator. We call this spin by topological insulator because we don't have can name this invariant, but we have spin by points in the spin spectrum. And actually, we also use the tool to characterize antiferromagnetic materials, because in some antiferromagnet, this collinear antiferromagnet, the C component should be a good function number. And this is the first, we know that this is the first magnetic topological insulator. And we characterize this with one spin by indicator. We have one spin by point. Even if the material doesn't have time reversal symmetry, they have time reversal combined with correlation, it's possible to use this tool to characterize this kind of material. Okay, so I'm going to finish. Finally, we took this material for the Nature paper to test our results. We, for example, bismuth bromide have bandgap energy in the spectrum, but also bandgap in the spin spectrum. But when we calculate the spin Hall conductivity and the spin average extinction number is different to 0. It's 4 for all cases. And when the spin starts to rotate to C to mu C, we notice a change of phase in the material. that in the nature paper they call that is a new phase of they call PDRC phase. We are trying to understand with Bernardo what means this phase, but we can reproduce the same behavior. They are collecting the spin gap in different regions where the spin start to rotate. But actually we have these three different spin Hall effect that we saw with the spin continuity and also with average extinction. To finish, some conclusion, we find this new spin by points in topological insulators. It is really a way to characterize this kind of materials. And also, Marcio, and when we work with orbitals, for example, the carbon effect, we use only the spin to characterize the material, but also we can use another properties like orbital or spinor decoupling, for example, to characterize the spectrum of the material with other physical quantities. And we characterize the space with spin invariants and these spin vectors. And this is, I think, so is an open door to explore the topological material with the spin topology. And the average extinction number could connect the information of the topology material that is not possible with the spin conductivity. I hope that you enjoy the talk, and thank you for Bernardo, my collaboration. And